discussing coupling constant. So coupling constant is the actually it is the the gap between the splitted peaks. Okay, the chemists quantify the coupling spin coupling effect using something called coupling constant, and it is having the notation J. Now, what is this one? J tells us that the splitting is there, and this splitting is due to what type of neighbors. Are these neighbors are in the similar environment, or are these neighbors are in the different environment among themselves? Okay, how can we tell this? So here let us take an example. We have the compound 1,1,2 trichloroethylene spectrum, and there we have seen two peaks. One is a doublet and another one is a triplet. Now in the doublet, okay, the doublet, these are having what? It is having a J value of 6.1 hertz. Now 6.1 hertz, and we notify this one as 3JAB. What is the meaning of AB? A is the what? A is the parent nuclei, and B is the environment due to which it has been splitted. Okay, and this 3 means they are having a bond gap of 3 bonds. Like here it is 1 bond, 2 bond and 3 bonds. Similarly 1 bond, 2 bond, 3 bond. So therefore there is a gap of 3 bonds, and it is being splitted by the neighbor HB, and this peak is for HA. So it is having 6.1 hertz. Okay, this is hertz. Why? Because so this is due to the frequency. Okay, it is the x-axis is frequency, so it is having the notation frequency. It is due to the applied magnetic field, and therefore if the applied magnetic field is not very high, there will not be a splitting, even though we have different environment proton. Once we increase or we use a specialized or more powered NMR spectrometer, then we will get this type of splitting. Okay, in a low grade NMR spectrometer, there may not be splitting. Okay, in some cases, so you have to go for a superior type, superier quality. So now let us see the next one, triplet. Now here you see there are three. Splitting in the peak has been split into 3. Now, how do we say that it is being splitted by 2 protons, and 2 protons definitely, and these 2 protons are not in different environment, they are in a similar environment, because the J value is same. This J value is 6.1, this J value is also 6.1. Supposing we have here 6.1, but this J value is a different value, supposing 6.4, then what we will tell, it is being splitted into a triplet, but this splitting is due to 2 nuclei, and these 2 nuclei are in the different environment, they are not equivalent. So let us see this part. Let us see this part. Unlike the chemical shift value, the coupling constant expressed in hertz in the same regardless of the applied field strength. So I have already discussed chemical shift. What is the unit? It is the ppm. But coupling constant, it is the unit is hertz. What is the reason? Because it is due to the applied magnetic field. Okay, this is because the strength of the magnetic moment of the neighboring proton, which is the source of spin-spin coupling, does not depend on the applied field strength. Now here the spin-spin coupling, okay, the spin-spin coupling is actually is the reason due to which splitting is occurring. Okay, the neighboring nuclei which is having a spin, it is coupling with the adjacent nuclei, and due to which there is a splitting, and this is not at all dependent on applied field strength. But when we look closely at the triplet, okay, then what we see is that the coupling constant, the gap between the suffix is 6.1, the same as for the doublet. Now 6.1 in the case of doublet, triplet also having the same coupling constant. This is an important concept. What is the concept? The coupling constant 3JAB quantifies the magnetic interaction between JHA and HB hydrogen cells, and this interaction is of the same magnitude in either direction. So they are in the same, they are due to the two different nuclei, and one is splitting the other, and similarly the other is splitting the HA. B is splitting the A, and A is also splitting the B. So whether whatever is the direction of the interaction, the splitting is due to each other. The coupling constant 3JAB quantifies the magnetic interaction between HA and HB hydrogen cell, and this interaction is of the same magnitude in either direction. In other words, HA influences HB to the same extent that HB influences HE. So it is in the same, whatever is the direction, it is in the it is due to each other's influence. Okay, when looking at more complex NMR spectra, this idea of reciprocal coupling constant can be very helpful in identifying the coupling relationship between the proton sets. So that was what I was discussing. Now let us see. Coupling constant between proton sets of neighboring sp3 hybridized carbon is typically in the region of 6 and 8. So if you see a value 6.1, 6.5, okay, you have to understand it is due to the neighbors in the sp3 hybridized carbon. Okay, so both are sp. Now if you see a value of 11 to 18, okay, so with protons bound to sp2 hybridized carbons, coupling constant can range from 0 Hz, no coupling at all, to 18 Hz, depending on the bonding arrangement. Okay, like here it is the vinylic trans. Okay, they are having vinylic trans, so it is having 11 to 18. Whereas if it is vinylic cis, it can be 6 to 15. So in this stage it can be little bit confusing, because this is also line in 6.8, this is also line in 6.8, and here also it is having an overlapping region, that is 11 to 18, and 11 to 15 comes in this value. Okay, so it can be little bit confusing. However, the other informations like IR, NMR, UV, that will be really helpful in removing the confusion. Okay, now vinylic jam means vinylic but in the same carbon, jaminal. Okay, so here you see what is the bond gap. It is 2. One bond, another bond, so it is 2. So here you can have a value of 0 to 5. So therefore the range is from 0 to 18, 0 to 18 for vinylic. Okay, so similarly for vinylic hydrogen in the trans configuration, we see coupling constant in the range of 11 to 18, where this I have already read out, and it is as here terminal is 5 Hz, 0 to 5 Hz, only one means 0 to 5 Hz. Ortho hydrogen on the benzene ring, okay, couple at, they will also couple, whereas what is the position? It is ortho, means these positions they will also couple, so they will have a splitting. Okay, so here due to this each other there will be splitting. Okay, so therefore it can have different environments. Supposing this one, okay, this is having, supposing chlorine, so these are not in the similar environment, it is ortho, it is matter, so therefore these two will interact with each other because they are not equivalent protons anymore. Okay, and therefore they will split, and at that condition the coupling constant will be 6 to 10. Whereas if it is matter, it is 0 to 4, and if it is aldehydic, you see this will also couple, we will be having 2 to 3. So coupling constant is really helpful to identify what is the environment and where we are located. So here we have already tabulated all this, whatever we have discussed. So 4 bonds, and you know para cannot couple because it is having 1, 2, 3, 4, 1, 2, 3, 4 and 5. So the para will not be splitting each other. So CH coupling, you have already done this. In case of CH coupling means this and this will couple each other. So that is more complicated. This is also CH coupling. So here also you have a double bonded C, and it is even more having higher hearts. This is phosphate. Phosphate and phosphate can couple each other, okay, because these are NMR active nuclei. They are having active nuclei, and it has a spin, active spin. So therefore this is the table. Let us move to the next